Hi, my name is Sumedh. I work at LinkedIn. Been there for more than 3.5 years. And pretty much since day zero at LinkedIn, I've been trying to get LinkedIn's exabyte scale data lake onto Iceberg. So I lead the Iceberg strategy there. And over the period of time, I've created Openhouse, which is kind of like a control plane for managing Iceberg tables. And we are right now in our phase of migrating all the data in LinkedIn onto Openhouse and Iceberg. Jesus?
Thank you so much. So my name is Jesus. I'm part of Microsoft. I'm an engineering manager working on Fabric Data Warehouse right now. But previously, I was part of the Gray Systems Lab, GSL, which is the Azure Data Applied Research Group. And that's when we engaged and started working with Sumedh and LinkedIn team, and we did this work. So with that, I think we can get started. All right. So over the last decade or so, we've seen a steady shift, right? More and more organizations are moving towards data lake-centric architectures for a growing number of workloads. And one of the biggest reasons is flexibility. Being able to use the best engine for the job without having to move or duplicate data, right? This is a model that reduces silos. It will simplify pipelines and gives you better cost control. But for all that to work well, you need kind of a shared solid foundations, right? And that's where table formats like Apache Iceberg have become foundational, right, or key. They propose a metadata layer and a protocol that enable features like complex read and write transactions or schema evolution or time travel and many other features on top of the data lake storage. And then just as important are catalogs, right, which increasingly act as a coordination, governance layer, control plane across all these engines, helping to tie it all together. Now, if you've worked with Iceberg or some of the other table formats for that matter, chances are that you've run into some of these issues, right? Storage fragmentation, slow queries due to skew or small files, jobs that hit unexpected bottlenecks, and so on. These aren't necessarily new type of problems, but in modern data lakes, they show in much harder ways. Because now we have many engines, many users, and lots of concurrent jobs, and they are all interacting with the same shared data sets and infrastructure. And then, adding multi-tenancy, adding unpredictable access patterns, and possibly other factors, and suddenly even what you consider simple problems become a constant challenge. So one solution to these problems that I was describing, is to try manual optimization. But soon you realize that since modern data lakes are so dynamic and complex, manual optimization just doesn't scale, right? It's gonna take you just this far. We can rely on someone hand optimizing partitions or compacting files on a schedule or anything along those lines. You need to move towards, you need to move towards autonomous data services, right? Systems that are observant, predictive and proactive, and will help you with those tasks. And in a broader sense, we kind of lay out this type of vision for Azure data a few years ago in the paper that you see referenced in the slide. That vision applies across data infrastructure in general, not just data lakes, but here we wanted to apply to data lakes specifically, right? So once we decided to go in that direction, the question was, okay, where do we start? And together with our colleagues at LinkedIn, we decided to look into data layout optimization. Data layout issues, things like small files or skewed partitions or poor sort order, form a category of problems that will degrade performance and increase costs in the lake. And these are problems that will show up both across cloud or on-prem environments, and they will compound also as systems scale, right? So you have more data, you have more jobs, more churn. That's why we thought that layout optimization was a strong area to begin applying these autonomous techniques, since the end result would have a broad, measurable impact across the whole stack. And here is the agenda for today, what we'll cover today. We'll start by looking at how the small file problem, one of the challenges within data layout optimization category, shows up in practice at LinkedIn. Then we'll introduce Autocomp, that is our automated compaction system. We'll share results from both real deployments at LinkedIn and synthetic benchmarks that we run to gain further insights. And finally, we'll talk about what's next and the broader challenges that we think are worth tackling. So with that, Sumedh, you want to take it away?
Thanks, Jesus. So at LinkedIn, we are right now managing tens of thousands of Iceberg tables. And our journey, when we were scaling it, we saw a high proliferation of small files. Many of you have experienced issues with small files in different formats, like high cloud bills, unreliable applications. For LinkedIn, we saw both of these, and also like because we use HDFS. HDFS has some limitations on how many files you can have in a given name node. So once you start getting in orders of billions of files in your lake house, then you end up trying to like solve this. So for the rest of this talk, we're going to go deep into the small file problem and how do we solve that at LinkedIn with Autocomp. So before we go to the solution, let's try to see where this problem originates. So you have on the left side a very simple Spark application where a user is trying to read from a data frame and write to an Iceberg table. The way the data gets written to the storage is heavily controlled by the configurations on the right side. So let's take Spark for example. Spark has these bunch of configurations that can change the way the data gets laid out on storage. So let's say the first one, the shuffle partitions. It impacts your white transformations like repartition, group bys, and what that value of 200 means is you will end up having 200 shuffle partitions, 200 tasks, 200 output files, irrespective of the data size you want to be writing. Then a simpler configuration in Spark is Spark default parallelism, where it's used for direct writers, like you're trying to read a data frame and just mappers trying to write to storage. Here, the value of 100 would mean like, again, 100 files, 100 output files, and irrespective of size of data. And we saw this in practice, where a user thought that like in cranking up that value of this configuration will make their jobs run faster. And they were trying to set this value to 1,000 for 3 gigabytes of data being written. So imagine that's 3 megabytes files being written to your storage. And finally, the max partition bytes or the input split size. Users think that they will get better read load balancing when they are doing their Spark job. But in the end, if this value is set to say 64 megabytes, unless you do a coalesce or a repartition, then you would end up with files that are on averaging around the 64 megabyte. So as you can see, there are these permutations and combinations or knobs you can tune in Spark to like to control how the data gets laid out. And it kind of gets complex and like kind of diverts your data engineer from thinking about the business problem and like starting to worry about the infrastructure problems. Then there are genuine patterns where you cannot avoid small files, like streaming writes. We want like low ingestion latency. We are checkpointing every minute, 30 seconds, whatever your ingestion latencies are. Trino wants to like write as fast as possible, trading off query efficiency, comparing to making sure the files are rightly sized in the first place. And finally, Iceberg, because it has versioning support, this situation kind of gets exacerbated by the write amplification, because now when you update, it's a new version. So I don't want to paint a like it's not a mistake that small files exist. And the way I think about it is sometimes it's trade-offs, right? If you are a data engineer, you want to optimize for your job success and runtime, which means that you are not able to focus on the long-term health of the table, right? And then there are defaults, like I showed a bunch of Spark configurations. Each one of them come with reasonable defaults, but as we all know, one size doesn't fit all when it comes to default. And finally, the lack of visibility. So when an application owner is writing data, there is no tooling built around a good feedback loop between the writer job and the downstream impact it has on the table storage and query health. Developers often don't see query pain until much later, like it could be weeks or months and can't trace it back to a particular write job that happened months ago, right? So the tooling also is, there is a gap in tooling about having an observability around this small files distribution, metadata growth, or generally the need for compaction. So when the intent for the data engineer was, I want to write my job to be like parallel and efficient and as fast as I can. I want to throw more partitions so that Spark runs faster. I want smaller splits because I want better load balancing on reads. What is happening behind the scenes is even if the job succeeded, the cost on the storage is getting higher. So essentially, jobs were succeeding, like dashboards were green, but then there's something happening behind the surface which is not like being observed. It's quietly building up until like one day, like the costs become so high, application starts slowing down, the read starts slowing down, and one day like the query starts to fail and your table is bloated and it's not usable anymore. And we've seen this in practice, and it doesn't happen like immediately. It happens like built for time. So that's why it's death by 1,000 files. Iceberg has this neat procedure that allows you to do compaction, and compaction is something most organizations will do to merge these small files into larger files. However, the main challenge when you are running an Iceberg deployment of tens of thousands of tables, or even 100,000 tables, is essentially who's responsible for calling these the rewrite data files API. How much compute budget is available to you to run these compaction jobs? What are the candidate tables for compaction and schedule? Is rewrite data files a sufficient layout optimization strategy? Or given that you're spending your compute on compaction, maybe you can throw in sorting as well. So that kind of thing, the idea here is we don't want this to be pushed to the end users or the writers. This is something the system behind the scenes should do it for the end users. So here is how we formulated the problem statement, and this is what led to our collaborations with our colleagues at Microsoft GSL. So essentially the problem statement becomes, we want to perform a cost benefit analysis to select top K tables out of your tens of thousands of tables for compaction and ensure that they fit within a fixed resource budget. And to essentially like to solve this, like we thought about this as a multi-objective optimization, where we are trying to optimize multiple objectives which can have often conflicting goals. Cost and gain are usually two conflicting goals. Sometimes if you want to get more gain, you have to pay more. But here we want to maximize our gain of reducing the small file count while minimizing the cost of compaction. So on the left side, as you can see, the gain objectives are, we want to maximize small files, maximize query performance. On the other side, we want to minimize the cost of doing the layout optimization, and also there is a hidden cost, which is sometimes non-trivial, of operationalizing them with a team and maintaining that, right? So we frame this as a multi-objective optimization problem. And when you start framing this as this optimization problem, you want to have a selection criteria for like top K tables. In this way, you start looking at trade-offs, right? So on the right side, you have a bunch of scenarios that I'm sure there are more, but these are some of the scenarios that we start running into. So table A is a massive table, has many small files. It's super expensive to compact. But table B is small, has still many small files and cheap to compact. Or table C has a very high churn rate. Now, what that means is like you ran compaction, the user came and rewrote whatever you compacted, and then it's undone for you, right? So that's a wasted compaction effort. Or you're trying to run compaction, but that table never gets queried. So you're not getting any gain on the query performance. So that's what we mean when we talk about this as a multi-objective optimization. And there is no right answer to this. So there is, it's kind of a recommendation system that kind of recommends, okay, these are the top K tables and we should be compacting them. That's Autocomp. So Autocomp is open source. It's available in that repo, github.com, LinkedIn, Openhouse. And for the first version of Autocomp, we picked these two objectives to optimize the maximizing of small file count reduction and minimizing of compute cost. So when we think about this as a compaction, so it's not really a compaction problem. Like Jesus mentioned, like layout optimization is a spectrum of problems that you can tackle. You can handle the small files. You can say that, hey, my data should be ordered, sorted by a certain column, or should my data should be partitioned by a certain column, and so on and so forth. So it's a vast. So we looked at it as in a more holistic fashion and came up with these functional and non-functional requirements for this system, which can be extended to other use cases. So in terms of functional requirements, we said we want finer grained work units for compaction. So I've been talking about top K tables, but it can also be the case where you don't want to compact the entire table. You want to compact granular partitions in the table. So then the problem statement becomes you want to rank top K table partitions versus top K tables. Then we said we have to work within a fixed budget, right? We didn't have infinite budget to run compaction on all the tens of thousands of tables. So our strategy needs to pick rank tables, pick those top K, and like it needs to be under that budget. The K needs to be derived from what budget we have. And finally, periodic execution triggers. This is so that like end users don't have to worry about it. There is a system that behind the scenes is working on it. And in terms of non-functional requirements, we wanted extensibility to other layout optimizations. We wanted explainability. So that's why we went with simple math in terms of solving optimization problem and not throw this as a problem for ML to solve. Sorry if I've disappointed anybody, and this is not a ML talk. And cross-platform compatibility is something we were looking for because we didn't want this to work with just the catalog that we use at LinkedIn. It should be like portable to any Iceberg deployments or any other table formats. So the end-to-end workflow for Autocomp is designed on top of this OODA model, which stands for observe, orient, decide, and act. So you have a candidate, which is a table, and you observe statistics for this table. So you are like extracting tables, metadata, the query statistics, and all that, and dumping them in a table for you to analyze. Then essentially what the next step is to orient based on those statistics. So you're trying to derive traits. So a trait could be something like you want to minimize the small file count. So that is one of your trait. And you kind of estimate how much cost it's going to take to like compact those small files. So that becomes another trait that you have. So once you have these traits, you feed it into a ranking algorithm, which essentially ranks all the candidates according to their traits that you are trying to optimize for, and then like picks the top K, which you actually feed into the execution for the compaction. And the most important part is there is a feedback loop that tells like how much you varied from what you estimated to what you actually saw when you acted on doing something. So putting this into like the perspective of the deployment, so on the leftmost side, you have like you have the entire catalog of all the Iceberg tables you have. Yeah, the input to the next phase is all the data and metadata, all the statistics that we extract from the table. And then in traits, we estimate how many files we would reduce in the given table and approximate what is the compaction cost it would cost us. Then we run a scoring algorithm. We compute scores based on a multi-objective optimization function. So because these are two different dimensions, file count reduction and compaction cost, we normalize them using min-max normalization, and then we scalarize them, and then we have one score. And then it's all about sorting based on the score, and then picking the top K within the max compaction budget. And on the right side, you see the list of tables that we picked for compaction. So in terms of evaluation now, so before I jump into the charts, so this is being deployed at LinkedIn as part of Openhouse, and Openhouse is an open source control plane for managing Iceberg tables. We've been building this for over 3 years now. And right now it's scaling to about 50,000 tables, and by the end of the year we'll be at more than 100,000 and maybe hundreds of petabytes. So in a nutshell, Openhouse is essentially basically giving you the core Iceberg, the Apache Iceberg, and it's a catalog. It's an Iceberg catalog that's shown in the blue side. It integrates with the standard query engine. So the catalog is the REST catalog, and in addition to it being a catalog, it also has two kinds of management services. Like on the right side, you see the Iceberg maintenance service that you kind of need to make sure your health of your Iceberg warehouse is good. And on the left side, you have your traditional like data management services like retention, replication, and DLO, which is the data layout optimization, which we recently added, and we've been talking about that. So putting Autocomp to work at LinkedIn. So we started by plotting this chart of file size distribution. And essentially what we said is like, let's bucket by file size, which is less than 128, between 128 MB and 256, and so on and so forth. So when we started it, when we started our scaling journey on Iceberg, we saw the orange bar to be heavily skewed towards small files, right? So we didn't do anything. We just put Iceberg, and we had like Openhouse do the basic Iceberg maintenance. At that time, we had the orange bar heavily skewed toward 128. Now, after scaling to a few months, we started like hitting reliability issues in production. We started hitting the HDFS scale issues. That's when we picked some expensive tables, which were, when a query ran, the query was scanning tens of millions of files, and at the end, like the query was not able to finish for different reasons. The HDFS was timing out, retries were causing a thundering herd problem, and so on and so forth. So we picked those tables that had bloated, and we said, okay, we are going to compact them using the rewrite data file API on a schedule. So we did that. We had our golden set of tables running compaction every day. So we observed this month over month, and we observed that the state of this distribution chart was not changing with the manual compaction, which runs on a schedule for a fixed set of tables. And this is a pattern most of the organizations adopt, where they say that, no, I need to compact all my tables and I need to run it on a schedule. But then you get into this pattern where you are kind of leaving some gains on the table, and that's what we observed. And that's where we also had been thinking about how do we scale compaction to all the tens of thousands of tables. So that's where Autocomp was built and Autocomp was deployed, and we started seeing a drop and significant gain, because now every time compaction ran, it made dynamic decisions based on the state of our lakehouse. Based on the state of the tables, it picked the right tables for compaction, and then we started seeing the shift that we wanted to see towards the right, where the green bar is growing in the 512 megabyte range. This is another way to look at this. So on the x-axis, we have month of the Openhouse deployment, and then on the y-axis, we have some normalized values. The green line shows the file count growth, and the purple line shows the deployment size. So the file count was growing much faster than our deployment size. And essentially, the first checkpoint for us was the manual compaction that I talked about. We did see some bending in the file count growth, but the real bend came when we deployed auto compaction on the 9th month, and which did this variable schedule, ranked list of tables, and we started making globally optimal decisions at the whole lakehouse layer. So when you start compacting files, you also start seeing improvements on your file system operations. So some of the workloads suffer from doing too much file system operations, and you see timeouts. I think this is true for any storage system. Like if you are like doing a very aggressive retries and stuff like that. So we saw a drastic drop when on the fourth month, when that particular table, which was running query of tens of millions of files, we saw a significant drop on the file system operation. And then we have been seeing steady drop in terms of like file system operations after the auto compaction was deployed. This is something we also started measuring, but it's a really hard problem to measure also at a scale that we run at, and also because the diversity of the workloads that the lakehouse has to support. So this metrics in this chart talk about the key workload metrics. These are metrics like how many files we are scanning as part of the query, what was the cost of the query, what was the query time, what was the, and also like plotting it against the events when we ran compaction, and hence like files reduced. So as you can see in the chart, we see a very high correlation between workload characteristics and file count. So when compaction runs, file count goes down, and then when compaction has not run for a while, query cost goes up. So this shows that the file count is kind of like a dominant factor in your workload, and I don't think like we have a full visibility into this, but I think this was an interesting observation for one of the scan heavy workloads that we run on an every day for the whole warehouse. Now we'll move to Jesus, and he'll talk about the synthetic benchmarks we ran.
Thanks, Sumedh. Yeah, so like Sumedh was mentioning, in addition to the real world impact that linking will also run synthetic benchmarks, because there are things that are just hard to evaluate in production, especially when there is a lot of interplay between the different systems and components and so on. So what we did is that we mirror linking deployment running on Azure. So as you can see there, we deployed the Spark and Iceberg open source. We also deployed Openhouse on Kubernetes using the Terraform scripts that are part of the project. And in order to evaluate the system, we ran benchmarks with LST Bench. So LST Bench is a benchmark tool that we developed at GSL in order to evaluate table formats, different table formats. And what we did there is integrated with CAB. So CAB stands for Cloud Analytics Benchmark. What they did is that they took the Snowset, that are these publicly available traces of utilization of Snowflake clusters that they publish themselves. And what they did is taking synthetic benchmarks and try to mimic the same kind of load that you see in those servers, right? So once we integrated these two, what we could do is, evaluate kind of a very diverse and concurrent workload. So you would have, workloads that are kind of a constant load. So it could be like dashboards accessing your data, right? Or, some periodic ones, like, every hour a job is executed. You have also like short bursts, right? That could be someone opening the dashboard on their laptop in the morning or anything along those lines. And you also have large bursts that would be the maintenance jobs, like compaction and so on. And we store the data in ADLS, that is the data lake offering in Azure. So one kind of key takeaway from this slide is that everything that you see over there in terms of projects and so on is open source. So you can go out there and try it yourself. And let me show you at least one slide with some of the numbers that we gather in this setup. So it's kind of a busy slide, but let me walk you through it. So in the x-axis, what you have is the experiment time. So these are experiments that run for 5 hours. And then in the y-axis, you have execution time. And each of the candlestick bars, what they are showing is a minimum latency for the queries, 25th percentile, median, 75th percentile, and maximum time. And what you can see in the row, the charts in the upper row are only for read-only queries. Sorry, the ones at the bottom are for read-write queries, so inserts, deletes, and so on. And we do the experiment with 3 different modes of execution for Autocomp. One is no compaction at all, that's the blue. The green one, that is our multi-objective optimization, where each hour we are choosing the top 10 tables. And finally, the red one, that is a hybrid approach, where you might choose either tables or partitions, and you choose the top 500. So a few things to observe over there is that as you can see, obviously, execution times for the queries get faster as the experiment progresses when you are running compaction, but which is kind of intuitive. But also, very importantly, variance goes down, which means that performance is more predictable. That is something that users also appreciate. And also, you can see kind of the difference between the table and the hybrid approach, where you'll basically reduce the time faster by being more aggressive. So this is the kind of trade-offs that we're discussing about. Well, that's going to be probably a more costly approach than if you are taking a more kind of fine granular, like in the hybrid approach. All right. So with that, let's move on to next steps and open challenges. So like Sumedh was saying, we started with Autocomp, where we wanted to do multi-objective optimization. But even in the factors that we chose, right? We chose to maximize the small file count reduction, as well as minimizing the compute cost. There are other factors that we could also take into account, and that we are actually studying, like maximizing query performance gain, or minimizing the operational cost. Now, the challenge here is also how you are going to balance between those factors themselves, right? And we have also started studying and evaluating some ML techniques that could help us basically to tune, how the system performs. And balances between all those factors. But if you take a step back, really, our long-term vision is a modular data layout optimization engine, something that can reason about the layout holistically and adapt as workloads change. And that means maybe supporting things like auto-sort, auto-partition, auto-index, you name it, right? Each working towards improving performance and cost under specific constraints. And as we mentioned before, we want this to be extensible and should be interoperable with existing infrastructure, existing engines, right? But getting there won't be easy. There are still a lot of open challenges and big questions. To name a few, how do you schedule layout optimizations without disrupting workloads, right? That's something that we have not discussed here because of time, but it's something that we observe, for instance, when we were running the experiments, the synthetic experiments, and we were kind of stressing the system. You can actually disrupt, for instance, your grid workloads, right? So how do you basically coordinate compaction and grid policies across engines in the data lake? How do you build better cost models that actually reflect the workload realities, right? So we have a cost model that proved very effective for what we were doing and worked well. But at the same time, when we started looking at the numbers, we realized that in certain occasions, there was this kind of, there was a difference between what you were getting, your actual numbers, right? And what the cost model was telling you, right? So I think there are some improvements also that we can do there. And can we also start integrating learning-based strategies that adapt over time? I think that can also be interesting. So these are the kind of problems that we think that shouldn't be solved over and over again by every vendor, infra team, and research group. And that's why the call here is like, let's build it together. So if this resonates with you, we'd love to connect. Come chat with us after the talk or reach out to us directly. And that's all we have. We have more details also in the paper that you can find through the QR code over there. It will be presented at Sumedh in a couple of months. And that's everything. Thank you very much.